Hey guys, how are you doing this week? So I want to talk to you this week about star formation. By the way, before I mention that, if you have not watched my video last week, I posted a little bit late in the week on main sequence stars. Do please take some time to watch that, because it covers some pretty important stuff that will be really vital for understanding as we go along, talking about how stars die, how stars are formed, and the cool stuff that comes out of stars. Mainly black holes, neutron stars, things like that. But it's important to know what main sequence stars are and understand the basic properties before we go on. So again, go back and watch on main sequence stars before going through this. But so what we're covering this week is star formation. And it's actually really neat because we can look out there and we can literally see stars that are being formed. I have a bunch of pictures of that in this presentation here, but it's also kind of a near and dear topic to my heart because I spent a couple years in grad school actually doing this particular type of thing. I mean, I wasn't forming stars, but I was obviously looking out there and seeing, using astronomical data and actually seeing how these stars form and processing images that show stars being formed. So it's a really cool topic, and I want to basically highlight the main details and show a couple things. So show where stars form, and show how they form. And we'll get into some details about what are the biggest stars that can possibly form by these methods, what are the smallest stars that can form, and we'll touch on how long does it take stars to form, but what I am going to kind of sidetrack is where we find stars in the HR diagram. The book goes through in a fair amount of detail talking about how you can trace the evolution of stars as they form on this diagram. So I'll pass it along to the book to explain that. But again, the main idea is how and where stars form. Our understanding of what processes take place for a star to actually become a star. So just, I guess to start, where are these stars forming? So there's these things called giant molecular clouds. It's not really a clever name, it's just that they're giant. They can be anywhere from tens to hundreds or even larger light years across. They're molecular because they're made of, well, molecules. And they're clouds, just because they're big clouds of stuff. So these things are some of the most massive things in the entire galaxy. From a single giant molecular cloud, you can get more than 1,000 stars out of that. And actually, as it turns out, we think our sun and most of the other stars that are out there formed from something that used to be a giant molecular cloud. As it began to collapse and form stars, all of these stars formed at roughly the same time. So our sun and many of the stars around it actually have more or less the same birthday. Some of these stars have lived and died already, but the ones that are still around, most of the stars around us we think may have formed right around the same time as our sun. So this is an example of a giant molecular cloud. It's kind of the crappiest picture ever. Basically, it's just a big dark patch in the sky. And it's not that there's not stars here, it's that there's a cloud between us and all of those other background stars. Now, if this giant molecular cloud was not in our way, this whole picture would just be covered with all of these background stars. So what's happening is the light from these background stars is actually getting blocked by this very dense, very cold giant molecular cloud. So the problem is seeing these things. When we look and we see a cloud, we're actually seeing an absence of light. And that's a problem because we can only use light to figure out what's going on there. But as it turns out, there's another way of viewing these things. So instead of looking at the visible wavelengths that we can see with our own eyes, if we look at, say, infrared light, this infrared light, which is a slightly different type of light, it's the same exact thing. It's a electromagnetic propagation, big fancy words meaning that it's light. Except it's light we can't see with our eyes. We can see with different types of telescopes. If you have, say, night vision goggles, you're looking at the infrared part of the spectrum. So if we look in different types of the spectrum, we can actually begin to see into these clouds. And that's exactly what we do with infrared light. So same picture in visible light, where it's just a big dark patch, but infrared light. And so now we can actually see all of that light passing through that cloud from behind, and more importantly, we can actually see into the center of that cloud. So if there's something going on in the center of that cloud, we're going to use infrared light to look at it. We're not going to use visible light because visible light is blocked by these clouds, but infrared light is our main source of information for all of what's going on inside these star-forming clouds. And just another example, this is the optical view, the visible view that we can see with our eyes. And we see there's just kind of a dark patch there, a couple of very bright things that are probably the stars that are in the process of forming in this cloud. But now when we look in infrared, now we see this big patch of glowy stuff. And this is all that cloud and everything that's inside of that cloud, and we can see exactly what's going on inside of that cloud that we otherwise can't get much information from. And what we look for are very strongly embedded pockets, basically just little clumps inside those clouds where there's stars that are being formed. And we call these collectively stellar nurseries. This is actually the scientific term for it, stellar nurseries or star-forming regions. And we think what happens is, as maybe the first or the second or the first few stars form in this cloud, and we'll talk about how they actually begin forming, but as the first few stars start to form, what happens is they go through a phase where their temperature increases, and they start giving off this ultraviolet light. And as you guys probably know, ultraviolet light is bad for us. It's bad for life, it's bad for stuff that it hits. Because what happens is as that ultraviolet light hits, say, a molecule, it destroys the bonds between those atoms in the molecule, and it sends them off going their own way. So ultraviolet light destroys bonds between atoms. And that's what's happening in this cloud. As the ultraviolet light pours out from these brand new, very hot stars, it destroys the gas and the dust that's around it in that cloud. Some of that gas and dust goes on to form new stars. Some of it gets essentially evaporated and is pushed out of that cloud. But what happens is we start to form bubbles. As there's a bright star emitting UV radiation, it starts to basically eat away that cloud from the inside out. And so we start seeing these bubbles. Again, we can't see these bubbles when we look in the visible part of the spectrum because all of that light is blocked. But if we're looking using infrared light, what we can see are these big empty regions inside at the very center of these massive clouds. And we know these are caused by new stars that have basically been pouring out their light and destroying all of that gas and dust around them, or causing that gas and dust to come together to form even more stars. So anyway, here's some pictures of some stellar nurseries. Now what we see here is very bright glowing gas. But then here there's a region that's devoid of anything. And keep in mind this is an infrared image. So we couldn't see this in the optical. But what we're seeing here is some big bubble. We're seeing the bottom half of a big bubble. So what's most likely happening is there are very young hot stars in the center of this that are pouring out ultraviolet light. And we're seeing the edge of that bubble as it's forming. So it's basically destroying these molecules, and we see some patches here where that destroyed gas is beginning to clump together. Right there, right here. And so this is where new stars are forming as a result of the light pouring out from those other stars. And we'll see some more examples of this. So this is called the Eagle Nebula. So you can kind of see it. There's like the eagle head. I'm getting a phone call. I'm going to ignore that. But you can kind of see the eagle head there, and the two wings of the eagle, and its center or its backbone. Now let's look more closely at the center. So this is basically, you see kind of a double lobe bubble that's forming here. Sorry about that. If we zoom in at the center, let's look at this. So now we see we can actually see some stars that are literally in the process of forming. They're not quite real stars yet, we think, but the matter has clumped together. It's been able to survive that onrush of ultraviolet light, and instead it's sucked in all of that ultraviolet, or all of the matter that's been pushed away by the ultraviolet light. So right there, a very clumpy region, right there, right there. These three pillars right here. So this is all light that's been basically pushed out from the center of that big bubble, and it's now beginning to clump together and form brand new stars. And this is one of the, so at the very center of this, if you rotate it just, I guess, like this for you guys, this is a very famous picture called the Pillars of Creation. Right here at the center is what we think is one or a few brand new stars actively being born. Same thing right there at the center. You can kind of see the light escaping from these clouds right now. If we wait maybe a few million years or half a billion years, instead of seeing these regions where gas has been more or less kind of stripped away and all that's left is this, instead what we'd see would probably be a very bright star, and a very bright star. And maybe a couple others around here too. So we're actually seeing matter and dust being basically disintegrated away and turned into newly forming stars. Some more examples. This is, if you focus in on this thing right there, looks like a horse head. And this is actually called the Horsehead Nebula. And again, this is a region of gas and dust that's been left over from other stars around it that have begun to form. And this is kind of one of these unformed regions where if we wait long enough, most of this gas and dust will probably have collected together and formed stars. And one of my Orion Nebula, we'll go back to this, I think. But one of my very favorites, this was my very favorite professor as a grad student. This was his favorite nebula, and this is the Flippin' Bird Nebula. Hope you can see the logic behind that. Okay, so it turns out the phone call was nothing. So anyway, how do these stars form? That's the next question. So first of all, again, these giant molecular clouds are very big and very massive. And it's not just going to be one or two stars, but it's going to be a whole bunch of stars that form from these giant molecular clouds. So what happens is we have gravity, and gravity tries to pull everything inwards. And as gravity begins to pull on these big clouds, they start to fragment out. Little bits and little clumps begin to form out of these clouds, where there might be a little bit more matter that started with. A little bit higher density here, a little bit higher density there. And over millions of years, these slightly more dense regions begin to attract more and more matter to them. So now we have more dense, more massive, more gravitationally strong little patches, little fragments throughout this entire cloud. But at the same time, gravity isn't the only thing that's acting on this. So as gravity starts to pull things together, we also have pressure, which is pushing the molecules away from each other. As things get denser and denser, they get more and more pressure builds up. So pressure is working to stop the contraction, but gravity is working to make the contraction happen. And it turns out that there's actually, so these things are basically in tug of war, and this is a theme that we'll go back to. But this pressure, the outward pressure, is working against the inward gravitational pull throughout this entire process. And as it turns out, in order to actually build stars, you need at least 100 times the mass of our sun in that cloud to even begin the process of gravity forming these little pockets. If you don't have at least 100 times more mass than the sun already has, in the huge cloud there, if there's not that much matter in this whole cloud, gravity is never going to be strong enough to even begin the process of stars forming, because it has to overcome that outward pressure as it begins to fragment out and contract. So the point is, these giant molecular clouds have to have at least about 100 times as much mass as the sun if they're even going to continue on to form stars in the first place. And the more mass they have, the faster they begin to contract and form stars. They have more gravity, and so the whole process gets shorter and shorter. So the book goes on a bit of a sidetrack, and I'll basically try to sum this up. Why are the first stars different, or were the first stars different in the universe than the stars we have today? So as you recall from Chapter 1, and if you've heard about this on your own, the universe is about 13.5 billion years old. I think 13.81 according to the most recent figures. But about 13.5 billion years old. Our sun's only been around for about 4.5 billion years. So there's been about 9 billion years before our sun was even born. And the question is, if we look way back right before the Big Bang, or right after the Big Bang, we can't actually talk about before the Big Bang, but just after the Big Bang happened, and if there were stars there, what were those stars like? Turns out we actually have a pretty good idea. So the point is that right after the Big Bang happened, the whole universe just filled with heat and radiation and all sorts of other stuff. It was an extremely hot, violent universe. And the only things that could form in that were very, very, very massive stars. And the reason for that is that everything was so hot, the gas was so hot in the very early universe, that you had huge amounts of this pressure. The hotter you make something, the faster the molecules move, the more they bounce off each other, and the more pressure builds up. So in this early universe, we had huge amounts of pressure because the temperature was very, very hot. So the only way to overcome that huge amount of pressure was to have even bigger amounts of matter. So in this case, we would have to have at least 100 times the mass of the sun to form a single star, because all of that matter has to work together to overcome that very high pressure, and that becomes just a single star. If you had less than that amount of matter, it wouldn't fragment apart. It would just never clump together at all. But so you have to have at least 100 times the mass of our sun to even begin forming a single star at the beginning of the universe, because there was just so much of this pressure going on, because it was so hot. So we didn't have stars like our sun, which is a G-type star. We didn't have F-type stars. We only most likely had the very most massive O-type stars. And these things live and die within a million years. They create these huge supernovae. They create black holes. Some of these black holes they create when they blow up might have actually become the black holes at the center of galaxies today. These supermassive black holes we'll talk about later. So really cool stuff. But the point is, the biggest difference between stars today and stars way back at the beginning of the universe were that the stars at the beginning of the universe were much more massive because they had to overcome way more pressure to form stars. So, going back here, so let's say we have this big, giant molecular cloud that's fragmenting out a little bit there, a little bit there, a little bit there from pockets where there's a little bit higher density. And let's say the overall mass of that whole cloud is enough for these fragments to keep on contracting and keep on in the process of forming stars. So in this case, it's not just going to be a single star. It's going to be hundreds or maybe thousands of stars that form within this little cloud there, or within the big cloud. Each fragment, each little packet, is going to condense more and more. You might get a star, you might get a few stars, you might get a binary star system, a trinary star system, a four-star system from each of these little packets, dense regions. And again, for each of these little dense regions, there's also gravity pulling it in and pressure pushing outwards. And again, in each of these little packets now, which will eventually become single or multiple stars, there's a tug of war, gravity inwards and pressure outwards. As they begin to contract more, heat builds up because more and more particles are bouncing off each other more often. They start to move faster, they start to get hotter. So the denser it gets, the hotter it gets. And you have pressure building, but gravity contracting. So here's some examples of, so this is called a protostar, by the way, a star that's not quite there yet, but it's well on its way to becoming a star. And so here's some great examples of protostars in the Orion Nebula. This is right in the constellation Orion. If you have a decent telescope, you can actually see this. I just pulled it up on the Normandale telescope a couple nights ago. So each of these little things, if you zoom way in the infrared light, you can see these protostars, stars that are in the process of forming. They're contracting, they're starting to heat up. We can see them because they're hot and they're giving off light. But they're not giving off light because of nuclear fusion, like our sun and like any other main sequence star. They're giving off light just because they're so hot. As gravity contracts it, they heat up. So here's what happened. We have this big cloud. It fragments out. Now you have little sections, little fragments of that giant molecular cloud. So this is one cloud fragment here. And the thing is, these big giant molecular clouds all tend to have a little bit of rotation because they're rotated in the entire galaxy. Here's the center of the galaxy, these big clouds, which might be 1,000 light years across, but the whole galaxy is 100,000 light years across. So these clouds are kind of going around the center of the galaxy. They have a little bit of spin, so a little bit of angular momentum. And now each one of these little fragments also has a little bit of angular momentum. So it's showing a cloud fragment spinning around a little bit. That's what the blue arrows indicate here. Now as that fragment contracts, just the one small little bit of that, as it contracts, it keeps that spin. And actually, in order to conserve angular momentum, as it gets smaller, it has to spin faster and faster. It's kind of like a figure skater as he or she starts rotating around with their arms out. They're going more slowly, but as they move their arms in, they start spinning faster and faster, and that's what happens here. And it reaches a point that starts spinning so fast that it kind of flattens out like a pancake or like a pizza. If you throw a ball of pizza dough in the air and you spin it enough, it starts flattening out, and that's almost exactly what's happening here. So it forms what we call a protostellar disk, or a flat disk, that will eventually have the brand new star at the center of it and maybe possibly planets going around on the outside of it. And the cool thing is, for some reason, we're not quite sure exactly why, but we think it has to do with magnetic fields. As that disk starts to spin faster, as more and more matter collects at the center of it, and more is becoming hot and dense at the center, some jets start shooting out. Some matter and some light begins shooting out straight up above that disk and straight below that disk. We call these the protostellar jets. And the cool thing is we can actually, a few of these protostars, we might happen to be right in their line of fire. If we're far enough away, that's totally fine. But we can actually observe these, and there's some really cool objects to observe because they change in brightness very quickly, and they're extremely luminous. But so this is called the T Tauri phase. It's a weird word based on blah, blah, blah. But you can just refer to them as protostellar jet phase, where they're giving off jets as they suck more and more matter in towards the center, which will eventually become the star. And this happens right before, we think it happens right before they hit the main sequence, before they become a real star. So here's just some more examples of these protostellar jets. So this is that protostar that's almost ready to be a star, but it's giving off this big jet there. Same thing right there. Slight bit of a sidetrack. I actually met my wife at a conference on galaxies at Harvard. I was presenting something on quasars. She was presenting something on one of these type of things. So she's also an astronomer, and so also kind of near and dear to my heart. But these jets coming from newborn stars are pretty cool things. So finally, eventually, when everything contracts enough, and the temperature at the center of this protostar gets hot enough, when it reaches 10 million Kelvin, 10 million degrees Kelvin, that's the point, that's the critical temperature When it hits that, now nuclear fusion begins. Hydrogen begins converting to helium. And that's when we officially call it a star. It's no longer a protostar because a star has to have nuclear fusion. Once you have nuclear fusion, now you're a star. And so once we hit that 10 million Kelvin point, now you become a main sequence star, and your luminosity tends to level off, your radius, the star's radius tends to level off, and all of your properties remain more or less constant throughout the entire lifetime that you're on the main sequence, meaning your entire lifetime as a main sequence star. I'm talking here as if you are the star. Maybe you are. I don't know. But so that's the point. It becomes a main sequence star once it hits that 10 million Kelvin mark. So I had said that there's a couple questions we can ask. First, what are the least massive stars that can form? What are the most massive stars that can form? So let's talk about the least massive one. The least massive ones. The idea here is that we need gravity to condense that thing enough and heat it up enough so that we eventually hit 10 million Kelvin. Now, the more matter you have, the more gravitational pull it has, and the more likely it is to heat up and hit that 10 million Kelvin mark. Now, if you start with not even, so if that one fragment of the bigger cloud, if that one fragment doesn't quite have enough matter, the gravitational pull isn't going to be strong enough to eventually form it into that new star. And the idea is that gravity inwards has to overcome that pressure outwards. So if you don't have enough gravitational pull inwards, that pressure, as this thing does condense, it contracts, it heats up, you might reach a point that there's no more gravitational pull left to overcome that thermal pressure. So it turns out you need at least 8% of the sun's mass, or more, to eventually be able to overcome that thermal pressure. If you have less than this, what happens is you contract more and more, it heats up more and more, and eventually that heat prevents the star from contracting any further, and it prevents that star from getting any hotter. So it can only ever reach that 10 million Kelvin mark if there's more than 8% of the sun's mass to pull it together. And as it turns out, Jupiter was actually only about 80, so if Jupiter was 80 times more massive than it is today, it'd be a star. We might have a binary star system. Jupiter would be a star orbiting the main star, which is our sun. But so again, the point is we need at least 8% of our sun's mass for gravity to win out. Otherwise, that heat, or the thermal radiation, the thermal pressure, prevents the star from collapsing any further. Now, if this thing doesn't have that much mass, if it contracts, it heats up, but it never hits that 10 million Kelvin mark, it just kind of sits there eventually, and it slowly, over the course of billions of years, it slowly evaporates, and it gives off typically infrared radiation, and we call it a brown dwarf. So a brown dwarf is a dim, really cool object. It's basically a failed sun, a crappy sun, is kind of how I describe it to my class. And all brown dwarfs have a mass less than 8% of our sun. If they had a mass more than that, they would have heated up far enough to actually begin nuclear fusion. So that's the least massive stars that we can form, 8% of the mass of the sun. And here's some examples. When we look in the Orion Nebula, we can see many of these patches that just didn't quite have enough mass to eventually form their star. So all of these are brown dwarfs. They're very difficult to see, and you have to look in infrared light to see them because they give off very, very little visible radiation. But they're all over the place, actually. So what are the most massive stars that we can form? So in this case, something very different happens. Let's say you have a really big fragment of your GMC, of your giant molecular cloud. If you have a really massive fragment, it begins to contract extremely quickly, much more quickly than the smaller fragments. So if you have a really massive fragment of it, it contracts so quickly and heats up incredibly fast at the center. It doesn't reach that 10 million Kelvin mark, but it heats up extremely quickly, and the whole cloud is giving off huge amounts of radiation. And what happens is that radiation itself, that light that's giving off as it contracts, adds to the thermal pressure. So we have thermal pressure from the molecules bouncing off each other, but we also have light pressure. The light is pushing outwards on that gas too. And this only becomes relevant when you have extremely large chunks of that trying to form together. So if you do have extremely large chunks, that thermal pressure builds up, and more importantly, the radiation pressure builds up, that light trying to exit that region, that very hot, glowing region. So that radiation pressure might begin to overwhelm the gravity. So gravity is pushing it together, but when you begin getting so much radiation being given off inside that area, now that radiation actually literally blows that cloud apart before it can ever eventually begin to form these high mass, very bright stars. And turns out the cutoff line for that is about 150 times the mass of our sun. So if you're below that, most likely gravity is going to be able to overcome that high amount of radiation pressure, the large amounts of light trying to stop the cloud from condensing. So if you're at maybe 100 times the mass of our sun, 110, we don't see many stars above that. But the couple ones that we do, we know that their gravity was able to overcome that large amount of radiation pressure that built up as it was forming. But if you start with more than that amount of matter, it contracts, it heats up, and the heat and the radiation that's built up blow it apart before it ever even formed a star. So how common are these things? How common are the least massive stars? How common are the most massive stars? Turns out these extremely massive stars, the 150, 140, 130 mass stars times the sun, are incredibly rare. For every one of these high mass stars we get 10 times as many, or for every one of these extremely high mass stars we get 10 times as many high mass stars. And we get 50 times as many sun-like stars, between about half the sun's mass and twice the sun's mass. So stars like our sun are way more common than higher mass or extremely high mass stars. But as it turns out, the very most common types of stars in the universe are the very low mass stars. So it's much more likely that this big cloud of gas and dust will condense into many, many very small pockets. And only a little bit of that, maybe not at all, but only maybe one patch of that entire giant molecular cloud will form a high mass star, or an extremely high mass star. A couple patches will form stars more massive than our sun. Quite a few more patches will form stars like our sun, but the vast majority of that entire giant molecular cloud will end up going into M-type stars, or K-type stars, which are by far the most numerous in the entire universe. And turns out that our predictions about the highest mass stars and the lowest mass stars we can see agree exactly with the types of stars that we do actually see. We've never seen a star more than 150 times the mass of our sun. We've never seen a star less than 8% the mass of our sun. So our theory agrees with our observations, which is always good in science. So anyway, I do encourage you to read the textbook. This is sections 16.1 to 16.3. And as always, email me if you have questions about it, but I hope this helped. Bye.